Okay, so this lesson is on determining probabilities, actually using what's called a two-way table, also known as a contingency table. And when you see problems like this, maybe like on the AP test, they normally start off with, a survey was conducted, and here's, a table of the results of this survey. So I thought it would be a neat idea to actually conduct a survey with students, assuming that we're going to be in 12th grade. If we have students have access to a mobile device or a computer, we can create a very simple survey where we get two pieces of information from each student. They select their age, and then they select out of these three choices, which would you rather own? A car, a truck, or a motorcycle? They can just choose between those three things. So I chose the ages 16, 17, and 18 because I figured for 12th grade, maybe we might have, one 11th grader in there, 16, 17 years old. It's up in the air. Hopefully, there's no other age ranges here because we wanted to survey the entire class and just get those results. So once we are able to do that and use an app like our website, maybe like with Google or with SurveyMonkey or something like that, we can actually get those results. I'm assuming that there's 25 students in the class, and this table, again called a two-way table or a contingency table, is going to show all the results. And again, these are used in statistics to show we're studying two pieces of categorical data. We're studying, how old someone is, and then also their preference as far as their vehicle. And we're saying, if I was basically just going to let you have a vehicle, which one would you prefer? A car, a truck, or a motorcycle? So the results are right here in this table. When you see a table like this, if you don't see totals on the sides and then a grand total in the corner, and again, these on the sides are called marginal totals, then you want to go ahead and make those totals yourself. So I'm going to make an extra column and an extra row for totals. And so we're just going to do some addition across and then up and down. So let's see. We're looking for the total number of 16-year-olds. So this is, you're just adding 0 plus 1 plus 0. Regardless of their choice of vehicle, we're just adding up the total number of 16-year-olds. So in this case, it would just be 1. 17-year-olds, we're going to add this 10 plus 6 plus 2. That's going to give me 18. That's the total number of 17-year-olds in the class. 18-year-olds, we're going to add these 2 plus 3 plus 1, and that's going to give us a total of 6. So again, these are sometimes called marginal totals. Just remember that because they're kind of off in the margins. And we're going to do the same thing with these other categories. The vehicle preference. So it's car, we're going to add 0 plus 10 plus 2 to get the total number of students whose preference was for a car. For truck, we'll add 1 plus 6 plus 3 straight across. 7, 8, 9, 10. That's going to give me 10. And then for motorcycles, we have 0 plus 2 plus 1 to get a total of 3. We're going to get a grand total, which should be the same if I added up these totals across or these totals going top to bottom, because this is going to be the actual total number of students that were surveyed for this survey. So if it doesn't matter, you add this column or this row, we should get 25. I'm going to kind of circle this or put a cloud around this. That's our total number of students that are in the class that participated in this survey. So what we can do with this table and with using some of the rows and columns and the total numbers, the marginal totals, we have a series of questions where we can answer some basic probability and a little bit more complicated probability on if we select a student at random from this class of 25 students, and then we can do some probabilities, and we'll go through these questions all together. And so there's something really neat that I found out that I could do. Love Microsoft Word. I can actually split this so that I can see my questions down here and I can keep the table. So I can split my view. Perfect. So again, the table up here. Not too much worried about this survey question. I'll just go ahead and leave it alone. So again, yeah, we have all our results. We've done our totals. We got the questions down here in this bottom pane. It says a student selected at random. So one says, what's the probability that the student is 18 years old? So we pick a random student from the class. What is the probability that they're 18 years old? So what we're gonna be looking for is the total number of, oh really? Is this really not letting me draw anymore? Okay, maybe I don't want to do a split then. Oh wait, I'm on the table. Okay, I got it. Technical difficulties. The total number of 18-year-olds, that's 6. We added these up. Whether or not they're cars, trucks, or motorcycle people, we had 6 18-year-olds, and we have a total of 25 students in the class. So our kind of basic formula for probability is we're looking at the number of, we can call it here, the number of, I am tempted to use the word successful, probably not the best word, outcomes. So the number of successful outcomes over or divided by the total outcomes. Oops, running out of room. So that's a one-step problem. It just says how many total successful are, we're looking at this as a frequency. How many of these are 18-year-olds? So we have a total of 6. So that's just 6. Drawing down here. Out of the total number of students surveyed, which is 25. Now we can write probability as a fraction, and we can just leave it like that. And of course, if we can reduce the fraction, we want to reduce it. You can also, type it to a calculator if you like decimals. I don't tend to prefer decimals, but 6 divided by 25 or 6 over 25 should get us 0.24, which we can also express as 24%. So again, if I randomly select a student in the class, there's a 24% chance that that student is 18 years old. Pretty straightforward. Number 2 says, what is the probability that the student prefers a motorcycle? So here, again, we look at our marginal totals, just like before. I'm looking at motorcycle, basically just this entire row. It was a total of 3 students that preferred a motorcycle as opposed to a car or a truck, out of a total of 25 students. So again, the number of successful outcomes over the total number of outcomes. So 3 out of 25, or 0.12, or 12%. Number 3 says, what is the probability that the student is 17 years old and prefers a car? So now we have this and operator. So we're really looking at the intersection of the column here for 17-year-old and the row of preferring a car. We're looking for the intersection of this column and this row. So that number is actually given to us right here in the table. These are 17-year-olds who responded to the survey that they prefer cars. So the number's kind of staring us right in the face. It's 10 out of the total number of students, 10 out of 25. It's going to give us 0.4 or 40%. All right, number 4 says again, and again, the premise here is I'm selecting a student at random. So number 4 says, what's the probability that the student is 16 years old or 18 years old? Now we have another compound statement here. We have an or connecting these two events or these two probabilities. So whenever we have an or, we have to ask ourselves, are the events mutually exclusive? And that's a good keyword here. Mutually exclusive means that two events can't occur at the same time. So what I mean is, it's impossible for a student to be both 16 years old and 18 years old at the same time. So because they are mutually exclusive events, when we're dealing with the or operator, we take the probability of this event, that they're 16 years old, we add it to the probability that they're 18 years old, and that's it. And we have our answer. So or, in this case, just becomes a plus sign. So let's do the probability that they're 16 years old. That again is in this total here, we only had one 16-year-old in this class. So 1 out of 25 total students. That's the probability of 16 years old. Plus, we're doing the probability of they're 18 years old. I think we answered that one earlier. 6 out of 25, because that was the total in this column. They both have the same denominator, so we can just add the numerators. We get 7 out of 25 is our probability. Again, we can leave it as a fraction. That's perfectly fine. Let's see, calculate it. If I wanted to do it as a decimal, which sometimes I do, looks like 0.28 or 28%. Now, if you take a look at number 5, it says, what's the probability that the student is 18 years old or prefers a truck? So this or makes you see or popping up again. It makes an appearance. The trick with this one, or it's not really a trick, it's just that these two events are not mutually exclusive on number 5. You can actually be 18 years old and prefer a truck at the same time. There were respondents to our survey that were 18 years old and preferred to own a truck. So with that, when we do have events that are not mutually exclusive, we do also add up the probabilities. Like we'll add up the probability that the student is 18 years old. We'll add that to the probability of the student preferring a truck. But we're going to end up subtracting basically where they overlap. And so that formula, we've seen that before. It's the probability of A or B, if we use the word or, is equal to the probability of A plus the probability of B minus the probability of A and B. So the probability that A and B occur at the same time. And this formula is actually true. It's also true for mutually exclusive events. Sorry, I skipped over. The thing is, so this formula is always true. The thing is, if two events are, again, mutually exclusive, then the probability that they occur at the same time, this P of A and B, is 0. That's what mutually exclusive means. It means they can't occur at the same time. So we would end up subtracting 0, and so that leads us to what we had done on number 4, was we just added the two probabilities together. So here we actually have to just do the same thing, but we're going to end up subtracting. So the probability that one of these, if we randomly selected a student that they're 18 years old, we're looking at our column for 18-year-olds. That's 6 out of 25. Now we are going to add, because we're using the word or, preferring a truck. Now again, we look at our row for truck, and we look at the total. It's 10 total respondents to this survey that preferred a truck. So we're doing 10 out of 25. But now we're going to subtract the and. So the number of respondents that are both 18 years old and prefer a truck, which is right here in the table, this 18-year, we just want to find out where the columns and rows match. 18 years old, prefers a truck, there's 3. So we subtract back out that 3 out of 25. And 6 plus 10, that's 16 out of 25. Take away the 3, we get 13 out of 25. And again, that's a perfectly valid answer, 13 out of 25. Or we can convert it to a decimal, so it's about 52%, or 0.52. So when you're using the word or, just make sure that you are checking whether or not these events are mutually exclusive or not. Remember, another word for that is disjoint. On number 6, we have, and number 6 and 7 are actually what are called conditional probability. It says, what is the probability that the student is 17 years old given that they prefer a car? They're 17 years old given that they prefer a car. So when it says given, I'm going to arbitrarily switch colors here. It's saying that we know that information. So we're really only studying respondents to the survey, students that prefer a car. So we're no longer interested in the entire class. Our total outcomes then changes from not being 25 like it's been on the rest of these problems. So we're only going to focus on ones that prefer a car, and then looking at ones that prefer a car, we're going to ask, well, what's the chance that one of them is 17 years old? So from the table, looking at the table, we go up here and we look at car, and I'm going to kind of outline this entire row here. So again, because it's a conditional probability, it says given that they prefer a car. This is like our entire universe here. We're no longer concerned about the people who prefer trucks, who prefer motorcycles. We're now looking at a total number of, the grand total of, like our denominator here is going to be 12, only 12, not 25. So we also look in that row that I've outlined in green, and it says the probability that the student is 17 years old. So the 17-year-olds that prefer a car right here are 10. So that's 10, but not out of 25. That's 10 out of 12, because again, we're only focusing on that one row. Whenever we have conditional probability, we're going to be only focusing on either one row or one column at a time. So 10 out of 12, this one does not come out to a really beautiful number. It's about 0.833 if you round, about 83.3%. So again, if you randomly select a student, that's the premise for all these, randomly select a student from this survey or from the class, if you know already that they prefer a car, what's the chance, what's the probability that they are 17 years old? So in that case, 10 out of 12. Now, I wanted to point out that on 7, it's flipped. We have something that looks almost like, if you weren't reading it correctly, it would almost look like the same question. It says, what's the probability that the student prefers a car given that they are 17 years old? It's flipped. So now we're given the information that this respondent is 17 years old. So now we're only going to focus on the 17-year-olds. In fact, that one column. Let me erase this. See if I can erase that. Sweet. And so I look at the column for 17-year-olds. This is like my entire universe now. So my grand total, my denominator, is going to be 18 instead of 25 because I'm only looking at 17-year-olds. Says what's the probability that the student prefers a car? So again, it's that same number for our numerator because that was the 17-year-olds that said that they prefer a car. That's 10. But in this case, it's not like number 6 where that was out of 12, because for that we were looking at the total number of students that prefer cars. Now we're focused on the total number of students that are 17 years old. So it's 10 out of 18. Our denominator changes. And this is approximately equal to it's a bunch of 5s. So I guess if I round it, it'd be like about 0.556 or 55.6% for my probability.